will happen. All right. You guys feeling pretty good about thinking about coral snakes, dangerous models? So one of the case studies in your book is this cuckoo case study, and your authors argue that this is actually a parasite-host arms race. Not a predator-prey arms race, but a parasite-host arms race. But as it turns out, in population and community ecology, when we build population growth models that we then adapt to look at the interactions of competitors, like we did back in evolution and ecology, where we have the Lotka-Volterra competition models, and also we build predator-prey models, which we didn't ever expose to you back in evolution and ecology. You're running two different models together, the predator model and the prey model. Things in one model appear in the other model, and that's how they get linked. Yes, ma'am?
What is the Lotka-Volterra?
Lotka and Volterra, Alfred J. Lotka and Vito Volterra were these two guys who, back in the 1920s, took the standard population growth models, which show you how the change in population given some change in time is determined by the intrinsic rate of increase of the population multiplied times the number of individuals that intrinsic rate of increase gets applied to. You can build a model that is really simple, that shows exponential growth as time increases from 0 to the future. Population size goes from 0 to a lot of individuals. And this is an exponential growth curve when you just have. How many of you took ecology with Dr. Judd? Did you guys go through these equations in upper level ecology?
Yes.
Yeah, okay. So you can alter this. What? Okay. You can adjust this. How can you adjust it, those of you who recently had ecology? Or if you remember from evolution and ecology. Is this a reasonable expectation that populations just continue growing and growing and growing?
No, you're gonna hit a carrying capacity.
So we can incorporate carrying capacity, so we can basically reduce the intrinsic rate of increase by the amount of the carrying capacity that is taken up by current population size. Now we have a population that is growing, and it grows just shy of exponential at the beginning, but as population size gets bigger and bigger, it starts to taper off and reaches an asymptote when population size equals carrying capacity, which is K. At which point, N equals K, this goes to 0, the overall rate of change goes to 0. It isn't that the population crashes, it's just that it doesn't change any longer. So this is a rate of change. How much does the population change given some change in time? Well, we can modify these further by including two populations. Population 1 interacting with population 2 such that population 2 reduces the carrying capacity of population 1 through competition. So we add a competition coefficient, and then we also have to have another equation where we have the growth rate of population 2, the carrying capacity of population 2 minus the effect of its own density on its carrying capacity, and the effect of the density of other population on its carrying capacity. And we run these two equations simultaneously to predict what happens when two species are competing with one another for a limiting resource. There's an effect, oh sorry, this is wrong, this is species 1. There's an effect that species 1 has on species 2's carrying capacity. There is an effect that species 2 has on species 1's carrying capacity. And the details of the numbers determine what the outcomes of competition are. In predator-prey interactions, we would have a predator population, and we would have a prey population. And each of these predators and prey rate associated with them, but this thing that was R times N, R is determined almost exclusively for predators by how many prey are hanging around. And so R gets expanded out into, and I'd have to go and look up, because I don't teach these models very often, I would have to go and look up the specifics of it. But R is, well, let's see. Or do I need to go look up? Can I just create it from first principles? I can't create it from first principles. But the rate at which the rate at which the predators grow is determined by the functional response as prey density goes up, the number of prey captured goes up, whatever shape that takes on, whether it's a type 2 or type 1 or type 3 curve, those prey get translated into the production of new predators through the numerical response. So both of these things are essentially tied to how predators, the rate at which predators find prey, eat those prey, and convert those prey into the production of new predators. And the prey population gets reduced by how effectively predators are cropping prey. So when we think about predator-prey interactions in a community ecology sense, we think about effects of predator and effects of prey acting on one another, but the same mathematical models that we use for modeling predators and prey, we can use those same models for modeling the population dynamics of parasites and hosts. It ends up being the same thing. And so if I wasn't planning on trying these out, but I can get these formulas for you if you're interested in them. That was a long aside for not much bang for your buck. So anyway, so we're dealing with parasites and hosts in a predator-prey arms race chapter because parasites and hosts interact the same way that predators and prey do. Parasites sap resources from the host. Essentially, they're losing nutrients and energy as a result of this. The only difference is that parasites generally are not lethal, but parasites do have potentially fitness costs that are incurred upon the predator, the host, because of the activity of the parasite. So in cuckoos are these birds that live in Europe. The famous cuckoo clock is based on them. And these are things called brood parasites. What do I mean when I use the term brood parasite?
They parasitize in the nest, because they're like deposited in the nest.
Yep.
As an egg, and they hatch and kick everybody's out.
Yep, the female cuckoo will come in, they'll remove an egg from the host nest and lay one of their eggs in place of the host egg. And then that egg develops much more quickly than the host eggs. That bird hatches earlier, and as soon as it hatches, it kicks the other eggs out of the nest using its wings to basically lever the eggs over the side of the nest, so that it is now the only bird in the nest, and then the host bird goes and feeds that animal. So here is the cuckoo, the gigantic cuckoo, removing a host egg, lays one of its eggs in the nest. The cuckoo, the giant cuckoo chick, hatches. This is the cuckoo with a host egg on its back, wedged between its wings, pushing it out of the nest. Does that to all of the other 3 eggs that are remaining in the nest. And then the poor little bird is now feeding this gargantuan cuckoo, and the bird doesn't have the good sense to know that that's not one of their own offspring. And so you end up, the host bird loses all of its reproductive output for that reproductive bout as a result of having this brood